All right, in this video, we are going to talk about a computational formula for the dot product. Remember, we defined the dot product of vector u and vector v by saying that it is equal to the magnitude of u times the magnitude of v times the cosine of the angle between the two vectors. Sometimes it's difficult to figure out what the angle between the two vectors is. And so that difficulty is going to lead us to this definition of the dot product. And here you can see if I have two vectors, u and v, and their components of u are u1 and u2, and the components of v are v1 and v2, then the dot product of u and v is u1 times v1, the product of the first components, plus the product of the second components. And it's very similar for space vectors. It is the product of the first components plus the product of the second components plus the product of the third components. Okay, so you can see that is really much easier to use than the other geometric based definition that we use. But I think it's important to understand the geometric definition of it as well as this computational formula. So now, where did this come from? It looks a lot different than the other definition that we talked about. So naturally, you should be suspicious. Hey, why is that the case? Why are these two things the same? And I'm not going to run through it in this video, but the equivalence of those two formulas, you can prove that it's true by using the law of cosines from trig class, okay, and show how that comes out. And it's pretty straightforward. But again, I'm not going to go into that in this video. All right, let's take a look back through the examples that we had before. All right, so last time, or in a previous video, right, we talked about the dot product of these two vectors, okay? And so now u and v. So now we're going to use this computational formula to do that. So we're going to take the dot product of u and v. And so it would just be 1 times 0 plus the product of the second components. That's 0 times 1. And then plus the product of the third components. That's 0 times 0. All right, so that comes out to be 1 plus 1 plus, oops, sorry, no it doesn't, 0 plus 0 plus 0. All right, and if you add all those up, it comes out to be 0. So that's exactly the same as what we did last time. Okay, same results. And this is much better because we can just go by the components. We don't have to, last time we just kind of looked at the two vectors and graphed them out and said, hey, they're perpendicular to each other, but here, right, we don't need to worry about that at all. So it's a much better situation. All right, in the next example, we have that we did this example previously. And in this case, we want to find u dotted with itself. So that's going to be 3, 0, 1 dotted with 3, 0, 1. And so that's going to be 3 times 3 plus the product of the second components, 0 times 0, plus the product of the third components, 1 times 1. And so it's going to be 9 plus 0 plus 1, which is equal to 10. Okay. And that's exactly the same result that we got by using the other definition of the dot product. So you can see it's giving us equivalent results. And so moving forward, most of the time when we're computing the dot product, we will want to be using this computational formula. All right, there are some properties of the dot product that we might have occasion to use here. So I'm not going to go over all of these, but You can see we've already talked about this one before here, that the dot product of a vector with itself is the magnitude of that vector squared. But the dot product does satisfy these formulas here. The dot product is also going to lead us to a nice formula for the orthogonal projection. Remember, we talked about the orthogonal projection. All right, and so this time using the formula for the dot product, we can come up with a nice, neat way of formulating that. So let u and v be given vectors. The orthogonal projection of u onto v is denoted by this notation right here, and it's PROG for projection. And then the vector that you're projecting onto is a subscript of this proj here. And then the vector that you're projecting is u. So that's u onto v is how I like to think about it. Okay. So we're taking the projection of u onto v. All right, and the formula that we're going to have for that is this scalar right here. This is a scalar, u dot v. Remember, that's a scalar when you dot two vectors. So u dot v on the top. On the bottom, we have v dot v, which remember is equal to the magnitude squared, right, of that vector. And then we're going to take that scalar and scalar multiply it times the vector v. Okay. Obviously, v can't be the zero vector for this to work, right? Because the magnitude of the zero vector is going to be 0, and then you're going to be dividing by 0, which is undefined. Okay. So now, where did this formula come from? This formula results from multiplying the unit vector in the direction of v by the length of the orthogonal projection. Okay. So let's see if we can take a look at that. And we'll just look at it in the simple case where we have u and v. All right, and then the orthogonal projection. We would drop this perpendicular down to v. And then the orthogonal projection would be this vector from here to here. Okay, and so to get that vector, what we're going to do is to, like this thing says here, we're going to multiply the vector in the unit vector in the direction of v. All right, and so that would be the unit vector in the direction of v would be this vector right here. We would take v and divide, right, by its magnitude. So that's going to give us another vector, a unit vector in this case, that points in the direction of v. So that would kind of look like this, like so. Okay. And then what we could do is, if you draw this as sort of a triangle, this triangle formed by u, the orthogonal projection, and this perpendicular. So here's u, here's the orthogonal projection, and here's the perpendicular. All right, what we need or want is this distance, right, from here to here. What's the length of the orthogonal projection? All right, and so remember, this would be theta in here. Ooh, man, this didn't turn out well. So this would be theta, this angle in here. I'll tell you what, let me redraw this because I didn't draw it big enough. So this would be the orthogonal projection. This would be u up here. And this would be the perpendicular. Okay, so here's theta. This angle right here. And on this triangle, the length, right, of u is the magnitude of u. And what we want to do is to find this distance right here. Let's call it just x for the time being, right? So if you just do some triangle trig, right, it says a triangle trig would say that the cosine of theta would be the adjacent. That's the length of this over the hypotenuse. And the hypotenuse would be the magnitude of u. And then you just multiply both sides by the magnitude of u. You're going to get the magnitude of u times cosine theta equals x, right? So that's the length of this. So if I take this magnitude of u times cosine theta, right, and times that by the unit vector, so I'm scalar multiplying now. Oops, let me do that on the other side. Actually, I'm running out of room here, so I'll just do it on this side. Even though, so this is just scalar multiplication, which we usually are used to writing on the left. But I'm going to write it on the right because I'm running out of space right here. So this is what I get when I do that. Okay. So this formula, this is going to be, right, the length of the or the vector, or the vector of the orthogonal projection, sorry, is what it's going to be, okay? And now why is it going to be the orthogonal projection? Well, remember this vector, right, this unit vector points, this little green vector points in the direction of the vector v, and it has length 1, right? And then I'm scalar multiplying it by the length of the orthogonal projection. So this vector has the same direction as the orthogonal projection, right? It points in the direction v, and it has the same magnitude as the orthogonal projection that we got from trig. The magnitude will be the magnitude of u times the cosine of theta. So this vector, right, this expression that we have right here, has the same magnitude and same direction as the orthogonal projection. So therefore, it is equal to the orthogonal projection, okay? And so this formula will do it. And now you may say, hey, well, that's not the formula that you have here. And so we can rearrange this formula if we do two things. If we multiply top and bottom by the magnitude of v, and again, v can't be the 0 vector here, okay? All right, so now I'm just going to do some rearranging of these things right here. And I'm going to write all the scalars out in front because that's normally what we're used to doing. So the magnitude of u times the magnitude of v times the cosine of theta. And then these are also scalars here, magnitude of v times magnitude of v. And then finally, I am going to put this vector v out in front over here, or out to the right over here. All right, all these are scalars, right? That's a scalar, that's a scalar, that's a scalar, that's a scalar, that's a scalar as well. So I'm just kind of grouping all those together over here. And then v is the only vector here. So we have a scalar multiple of v. And there we go. And now you might recognize, hey, this is just the formula. This is just how we define the dot product of u and v. Magnitude of u times the magnitude of v times cosine theta. And so we can just write that top part as the dot product of u and v. And that's kind of nice because then we don't have to worry about finding the angle between the two vectors to calculate this orthogonal projection. All we need are the components. And then down here I have the magnitude of v times itself. That's the magnitude of v squared, right? And remember we said that is also the dot product of v with itself. And then that's a scalar, right? Because the dot product is a scalar over a scalar times the vector v. And you can see that is the formula that we have for the orthogonal projection. So that's where that formula comes from, okay, for the projection of u onto v. All right, and so now to calculate the orthogonal projection, we just would do this, and it's nice and neat. uh, rather than having to go through it every single time. All right, let's do an example where we use that. So here we have two vectors W, which is 3, 1, 2, and X, which is 1, 0, 1. And we want to find the projection of W onto X. Okay. Okay. And so on the top, right, remember the formula for the projection, right? We're projecting U onto V, right? This is a UV over the dot of V times V itself. In this case, right, the thing playing the role of U is W. That's the vector that we're projecting, and we're projecting onto X, right? So you just got to make sure that you're doing this in the correct way, because if you do reverse those, you will get a different answer potentially. So in this case, it's going to be W dot X over X dot X times the vector X. Okay. All right, and then just run through that. So W is 3, 1, 2. Actually, I'm just going to do this off to the side. It's a little cleaner that way. So over here, we'll do W dot X. That's going to be 3, 1, 2 dotted with 1, 0, 1. So that's going to be 3 plus 0 plus 2. Right, 3 times 1, 1 times 0, 2 times 1, and then add those together, we get 5. And then X dotted with itself. So that's 1, 0, 1 dotted with 1, 0, 1. So that's going to be 1 plus 0 plus 1, right? 1 times 1 is 1. 0 times 0 is 0. 1 times 1 is 1. That's going to come out to be 2. All right, and then going back to the formula for the projection, right? This number on top is a 5. This number on the bottom is a 2. And then we are projecting that, our scalar multiplying that times X, which is 1, 0, 1. That comes out to be 5 halves, 0, and 5 halves. Okay, and I thought I had that as a solution on there. Yeah, I guess I do. Okay, so here you can see that if you take a look at this link. All right, there is the vector W. And here's the vector X. Okay. And we're projecting W onto X. So in this case, X, right, we would have to kind of extend it out with a dotted line to right about in here, right? And then we would be dropping the perpendicular, right, from W onto that extension. And then the projection would go from the initial point of X, right, out to that place where the perpendicular meets the extension. And you can see that is right there. So you can see that looks just about looks, exactly what the projection, right, of W onto X should look like there. Okay, so I think that's it for this video. In the next video, we are going to talk about orthogonal decomposition of vectors.